Hello, and welcome to my YouTube channel called Statistics from A to Z, Confusing Concepts Clarified. These videos are based on content from my book of the same name, which is published by Wiley. For more information on the book and these videos, please visit statisticsfromatoz.com. This video is one in a playlist on probability distributions. The playlist is planned to include a 3-video series on distributions as a whole, plus individual videos on 9 different types of distributions, as well as a couple on the topics of the properties of distribution. See statisticsfromatoz.com/videos for the latest status of this work. You may find it helpful to view the first 2 videos before viewing this one, but that is not a prerequisite. As usual in the book and in these videos, we'll go quickly through a list of keys to understanding, or KTUs, to give you the overall picture on one page. And then we'll go into detailed explanations of each of the keys. For this video, there are 6 KTUs. The first key to understanding is the binomial distribution is used with discrete data. It displays the probabilities of counts of outcomes of binomial experiments. Units are counted, not occurrences. The second KTU says, in a binomial experiment, there are a fixed number of trials, n, and each trial can have only one of 2 outcomes, yes or no. The probability P of a yes in each trial is the same for all trials. Each trial is independent of the others. This means sampling is done with replacement. Key to understanding number 3 says, there are different binomial distributions for different values of n, the number of trials, and p, the probability of each trial. The fourth key provides formulas for the mean and the standard deviation of a binomial distribution. The fifth KTU says, the binomial distribution is useful for solving problems of the kind, what is the probability that a sample of 10 units will include 2 or more defective units? The final key to understanding says, under specific conditions, the binomial can be related to the hypergeometric, the Poisson, or the normal distributions. And here on one page are all 6 keys to understanding the concept of binomial distributions. You may wish to pause the video at this point and read them all together. Key to understanding number 1 begins by telling us that a binomial distribution is used with discrete data. Discrete data was described in the video Probability Distributions Part 2, how they are used. Briefly, discrete data is usually count data. The horizontal axis of the graph of a binomial distribution shows the counts. Counts are non-negative integers like 0, 1, 2, etc. The probability of that count is shown by the height of the bar above it. Here we show 3 different binomial distributions. We'll explain later how the different shapes are determined. KTU number 1 goes on to say, it displays the probability of counts of outcomes of binomial experiments. And finally, KTU number 1 says that units are counted, not occurrences. If we want to count occurrences, we would use the Poisson distribution instead. The binomial distribution is used for counts of units, such as the number of shirts manufactured that have defects. Units are different from occurrences. If a shirt, which is the unit, has 3 defects, we would add only 1 to the count of defective units, defective shirts, and we would use the binomial distribution. If, on the other hand, we were interested in the total number of occurrences of defects, not the number of defective units, we would count 3 occurrences for that 1 shirt, and we would use a different discrete distribution, the Poisson distribution. Key to understanding number 2. In a binomial experiment, also known as a Bernoulli experiment, there are a fixed number n of trials. A coin flip would be an example of a trial. B, each trial can have only one of two outcomes. In my book, the two outcomes are called yes and no. Most others call the outcomes success or failure, but that can be confusing when the thing being counted is bad, like a defect. A defect would then be called a success. C, the probability P of a yes in each trial is the same for all trials. Note this P is a different concept from the P, also known as the p-value, which is compared to alpha in inferential statistics and hypothesis testing. Both P's are probabilities, but p-value is the probability of a false positive error in hypothesis testing, and this P is the probability of a yes in a trial. D, each trial is independent of the others. The outcomes of previous coin flips have no influence on those that follows. That is, each trial is independent of the others. If you get 10 tails in a row, the probability of a yes ahead in the next coin flip is still 50%. So each trial is independent. The concept of independent trials is related to the concept of sampling with replacement. To illustrate this, let's say we're doing a study in a small lake to determine the proportion of lake trout. Each trial consists of catching and identifying one fish. If it's a lake trout, we count one yes. The population of the fish in the lake is finite. From our boat in the lake, we have no way of knowing this, but let's say that there happen to be 100 fish in the lake, 70 lake trout, and 30 rainbow trout. If we catch a lake trout and then throw it back before trying to catch the next fish, that is called sampling with replacement. Each time we drop our line to catch a fish, which is one trial, the probability of catching a lake trout remains 70%. This is because there are still 100 fish in the lake and still 70 lake trout. The probability of each trial does not depend on the outcomes of any other trials. The trials are independent of each other, and that is a requirement for a binomial experiment. On the other hand, sampling without replacement, that is not returning the fish, changes the number of fish in the lake and the probability. As the table shows, if our first trial catches a lake trout and we don't replace it, then the total number of fish in the lake changes from 0 to 99, and the total number of lake trout changes from 70 to 69. This causes the probability P to change, and that causes the trials to not be independent. So we would not have a binomial experiment, and so we cannot use the binomial distribution. We would have to use the hypergeometric distribution instead. See the video on hypergeometric distributions. Sampling a population or process that is infinite is also considered to be sampling with replacement. An ongoing process, like continuing to flip coins, can be considered infinite. The probability P does not change. KTU number 3 says there are different binomial distributions for different values of n, the number of trials, and P, the probability. There are infinitely many distributions in the family of binomial distributions. There is one for each combination of the values of n and P. In these graphs, the horizontal axis is the count of units, denoted by a capital X. The vertical axis is the probability of that count, denoted by P of X. These three graphs show the effect that P has on the binomial distribution. For P equals 0.5, or 50%, the middle graph shows that the distribution is symmetrical about the mean. For P less than 0.5, the mass of the distribution is on the left and the tail is skewed to the right. P greater than 0.5 has the opposite effect. These graphs show the effect of varying n, the number of trials. Increasing n moves the center of the distribution to the right. It also adds more bars for the additional value of x. The narrowing of the bars in the graph on the right has no meaning. It's just what needs to happen in order to fit more x values in a graph of the same physical width as the one on the left. Note that the distribution on the right is starting to look like the normal distribution. More on that in KTU number 6. The first part of KTU number 4 says that the mean, mu, of a binomial distribution is equal to n, the number of trials, times p, the probability of each trial. Without knowing anything about statistics, if you were to flip a coin 30 times and you had to guess how many heads there would be, what would you guess? Most people would say 15. Intuitively, they calculate n times p. For n equals 30 times p equals 0.5, you get np equals 15. You know that it may not be exactly 15, but it would most probably be close to 15, and on average, you expect it to be 15. So it makes intuitive sense that the average or mean of a binomial distribution would be np. The leftmost graph illustrates this. Mu equals 15, and counts close to 15 also have high probabilities of occurring. In the middle and right graphs, we keep n the same at n equals 10. Then if the two p's are 0.1 and 0.9, the graphs are flip sides of each other. This also makes intuitive sense. The standard deviation of a binomial distribution is the square root of the quantity np times 1 minus p. The first thing this formula tells us is that the standard deviation grows larger as n grows larger. This makes sense because if n equals 5, then the possible counts, the x's, can range only from 0 to 5. If, on the other hand, n equals 30, counts can range from 0 to 30. The effect of p times 1 minus p is less intuitive, but we can see from the table that the largest values for p times 1 minus p are produced when p is closest to 0.5. So the standard deviation of a binomial distribution gets larger as p gets closer to 0.5. KTU number 5 says the binomial distribution is useful for solving problems of the kind, what is the probability that a sample of 10 units will include 2 or more defective units? Let's say a process has a historically produced products with a defective unit rate of p equals 0.02 or 2%. We take a quick sample of n equals 10 units and we find 1 unit is defective. So our sample has a defect rate of 10%. Should we start worrying that our process defect rate has changed? We would want to know, what is the probability of 1 or more defective units? That is the probability of x equals 1 defective unit plus the probability of x equals 2 defective units, and so on through the probability of 10 defective units. More simply, it is 1 minus the probability of 0 defective units. From a table or software, we can find that the probability of 0 equals 0.817. So the probability of getting 1 or more defective units is 1 minus 0.817, or 0.183. So we might expect a sample of 10 to have 1 or more units about 18% of the time. So it would not be that unusual to find 1 defect in a sample of 10. But what if we found 2 defective units? The probability of 1 is 0.167, so the probability of 2 more defective units is 1 minus the quantity probability of 0 plus probability of 1, and that turns out to be 0.016, or 1.6%. So 2 defective units in a sample of 10 should be relatively rare, and it might cause us to investigate further into whether our process is still operating within the historical defect rate. We said earlier that when sampling without replacement, we should use a hypergeometric distribution instead of the binomial. However, the binomial can be used as an approximation for the hypergeometric when the population size n, capital N, is large relative to the sample size, lowercase n. For example, when capital N is 10 times larger. This makes sense because replacement of a sample back into the population has a small impact when the sample is very small and the population is very large. The binomial distribution approaches the Poisson distribution as n approaches infinity while p approaches 0, keeping np fixed. The Poisson distribution is another discrete data distribution. It is used when counting occurrences, not units. Also, the binomial approaches the normal distribution as n approaches infinity while keeping p fixed. This was illustrated in a previous slide. Okay, that concludes our clarification of the concept of binomial distribution. If you liked this video, please remember to press the thumbs up like button on your screen below. I'll be making more videos of some or most of the 60+ concepts in the book if folks like you tell me that more videos are wanted. Please subscribe to this channel to be notified when new videos are uploaded. Also, the website statisticsfromatoz.com has a listing of available and planned videos. Now, videos like this one can be very helpful, but they're not very handy when you want to quickly look up something on the job while studying or during an open book exam. For that, nothing beats a book or an e-book. You can also learn more about those on the website. And I'd recommend following my blog at statisticsfromatoz.com/blog. I've got some things there that hopefully you will find interesting, like a Statistics Tip of the Week series, as well as posts showing that you are not alone if you're confused by statistics. I'll also be posting on the Facebook page, Statistics from A to Z, and on Twitter as @StatsA to Z.